Right, so our next speaker is Kauzo Johar.
Yes.
From Chiplets. And the title of his presentation is curiously titled SRAM Dead or Alive.
Right. But it's the last session of the day. Hopefully you're not dead and alive. So the title of the talk more specifically is SRAM Dead or Alive. If you know what an SRAM is, great, you'll learn a bit more about why it is dead or alive. And if you don't know what an SRAM is, hopefully you'll take away from this presentation what an SRAM is. So it should be useful for you. So who am I? I'm the founder of a company called Chiplets. A bit of my background, I've been a chip designer for all my life, close to 17, 18 years now. Most of it was for a company called ARM, designing microprocessors, and I had a bit of a stint before starting Chiplets. Let me start off with what is an SRAM. The basics first, which is it's a static memory, which means it doesn't need constant refreshing. I was recapping for people who just arrived. I'm talking about SRAMs. And if you know SRAMs, great. If you don't know SRAMs, you'll at least take away what an SRAM is end of today's talk. So what is an SRAM? Just to recap, static memory, doesn't require constant refreshing. It's volatile, which means the moment you take the power off, the contents of it is gone. And the traditional way of designing SRAMs is using CMOS transistors and a 6-transistor design. There are many variations of the memory where you can get 8-transistor, 10-transistor versions, 4-transistor versions, even someone claiming to have built a 1-transistor version of an SRAM, which is a lie, but they market it as a 1-transistor SRAM. But in the simplest view, it's 2 inverters cross-coupled with 2 transistors that are used to either write into those cross-coupled transistors, inverters, or to be able to read out the values from those cross-coupled inverters. So that's the most simplistic view of an SRAM cell. So this is one bit of information, and then you would connect them in an array. There's a lot of other peripheral logic, sense amplifiers and so on and so forth, which I've not gone into the details of, but that's roughly what a SRAM is. A brief history of how did SRAM come about? They're actually quite old, way before I was born. Back in the 1960s, it was invented by a company called Fairchild Semiconductors. There were 2 people in Fairchild. I'm getting some laughs in the audience.
Not that old in the 60s.
But yeah, two people in Fairchild. They coincidentally, they both invented SRAMs, but they use different transistor types. Moving on, what you'll see is in 1969, Intel launched their first ever chip, which was a 64-bit SRAM chip. 64-bit. Imagine what if you had 64-bit of SRAM in your pocket, and what you could do with that. So Intel, we know it as a microprocessor company, but actually its first ever chip was an SRAM chip. And they obviously went on to design microprocessors which use a lot of SRAMs. Fast forward to 1980s, SRAM becomes very commonplace and on the same die as your processor, as caches. And then SRAM became even more prolific in the 90s, where every ASIC you could imagine used SRAM in some form or the other. So it's tightly coupled memory, very much used for deterministic applications. There were many variations of SRAM. So in the 2000s, with the mobile boom, there were low power variations of SRAM, to bring the power consumption down of these battery-powered devices. And more modern versions of SRAMs use the latest transistor technology, so FinFET, and then moving forward, gate-all-around, and then obviously the roadmap continues. So you might take away from this and say, what SRAM is pretty much alive and kicking. So before I go on to dead or alive, why it has been so ubiquitous as a memory. it offers the best read and write latency. So if you look at how quickly you can access this memory compared to some of its peers, it's the fastest memory available. And so that's been the real feature of why SRAM has been used on the same chip as compute, because you can access it that fast. You can typically clock it at the same frequency or thereabouts the same frequency as CPU. And you don't really want to starve your CPU. You want to keep up with the CPU. So that's primarily why SRAM has been a very popular choice for CPU caches, but it's 100% deterministic. If you take a particular number of clock cycles to access it, you will take that many number of clock cycles to access it repeatedly. It's not like DRAM where there can be some non-determinism because of the refresh cycles. And the way it is easily integrated, so chip designers love it. They could generate any shape or size of SRAMs and put it onto their chip. Unlike off-chip memories where they come in fixed sizes, you have to work with them. So there are many reasons why SRAMs have been ubiquitous and very popular. Some famous designs, well, actually, could pretty much stand up with any design, and that would have a lot of SRAMs on it. But I picked some of them, which shows the amount of SRAMs that go on chip. Take this McKinsey 180 nanometer CPU, more than 50% of it is just SRAMs. And actually, what you don't see is there are more SRAMs in there, which are smaller macros, which have not been highlighted. But the chips are largely dominated by SRAM, not by the CPU switching, but by memories. However, SRAMs don't scale very well now. So if you have good eyesight, apologize, and if you squint hard enough, you will see that it's sort of stopped scaling in density below 5 nanometer. So in the most modern process nodes, you practically are not getting any scaling from SRAM. And that's an AMD Ryzen CPU, which is a very modern CPU. You can buy it and use it today. 50% of that is L3 cache. I mean, there are L1 and L2 caches, which are SRAMs as well. I've not shown for simplicity, but roughly 50% of this die is just SRAM. And if you were to keep transitioning these designs to more modern process nodes, and you're not getting any scaling benefits, you're paying through the roof for these dies in terms of the wafer costs, which I'll come to in a bit, for no benefit. That's the challenge that people are facing, which is people love the memory, but it's not scaling very well. So what's the potential solution? A potential solution is, why don't you take it out of the chip? If you look at the first microprocessor designs that use SRAM, the SRAM was on a separate chip, not on the same chip as the CPU. But Moore's law has been so friendly and kind that it was much beneficial or better to put it on the same chip. But I think where the trend is going is it's no longer beneficial to put it on the same chip, especially when you have really large memory macros. So what can you do? You could connect it if you happen to listen to the talk by ARM, a couple of talks earlier, where I talked about chiplet composability. One of the ways you could do it is build an SRAM chip and connect it via the UCIe interposer architecture. The problem with that is you would get like 50 to 100 nanosecond latency. Now, I said the reason why SRAMs have been ubiquitous is because you can access it with half a 1 nanosecond latency. If you're now going to put it on a separate die and then take 50 to 100 nanoseconds to access it, it just completely tanks your performance and defeats the purpose of having it. So what's the solution? It turns out that actually if you vertically stack chiplets, the interconnects are in tens of microns, which is roughly the length of wires on chip. A chip could be 500 millimeters square. That's quite large. So 10 microns is nothing in terms of interconnect size. So if you were to vertically stack them, you would get, again, in the order of half or 1 nanosecond latency. So very, very low latencies. So that's potentially a way path forward. Why now? Why now consider this as a chiplet approach rather than the traditional on-die approach? Well, chips can't get any bigger. Pretty much most of the high-performance compute chips have hit a physical limit called the reticle limit, about 700 millimeters square. Even if you wanted to put more transistors on it, you can't, because the equipments that are used to manufacture those chips just don't support a bigger size. Advanced 3D integration, which I talked about, have now got really high yields. The yields are as good as mature process nodes, so in the very high 90s. I'll come on to the wafer cost disparity as one of the reasons why now, and reliability and scaling issues. If you make something on a more modern process node, your yields are going to be down, and you're going to get even the SRAM design is less reliable. So there are more yield issues on memories compared to logic. So let's dive in a bit more. If you are someone who wants to consider this, that is basically, I want to use a lot of SRAMs, but not use it on chip, or what's the point where I should consider on chip versus off chip? And so there are three parameters you need to really consider. There's something called phi area, cost, and performance, obviously. So in terms of area, there is the cost you have to pay on your compute chip, which is the vertical interconnects. So there's an area that the vertical interconnects consume. And so as an example, if you wanted 300 IOs on a 7 nanometer process using a 9 micron page, a bit technical, that would consume about the same area as the 1 MB SRAM. Which means if you're using an SRAM which is less than 1 MB, I mean, there's no point in going off chip, because you might as well put it on the same chip. So that's the break-even analysis. This is just, it's not to scale, but just to illustrate. If you were to use a 16 MB cache, the phi area would be modest compared to the size of the macro, memory macro. So at those sizes, you're way beyond the break-even threshold for area. Cost. So these are, I would say, approximate numbers, because actual wafer prices are confidential. But as an approximation, it's relatively good. So if you were to just make SRAMs, nothing else, 128 megabytes of SRAM on different process nodes, in terms of capacity, is 128 megabytes, no different. But you end up paying more on old process nodes, because you still get scaling when you go down the process node, but you don't get any cost benefit below 7 nanometer. So if I had to make 128 megabytes of SRAM on a 2 nanometer, that would be almost, $11 is conservative. It's almost 3x the cost of making it in 7 nanometer. When you take the yields into account, because 2 nanometer is not at the same yield as 7 nanometer. So that's the break-even cost analysis you need to do, which is, my cost might be lower as well at this point. And performance. Performance is very subjective. So there's no formula really to come up with on what performance and how you would measure. Essentially, you want more performance, and you would unlock more performance by adding more memory, typically. But then the factors to consider are the latencies are not the same. There'll be some difference in latencies. You might actually reimagine your compute architecture. So the AMD die shot I showed you, all the CPUs were pushed to the corners, which means if a CPU wanted to talk to another CPU, it had to go through a lot of routing delays. Now, by taking the cache out of the die and vertical, all the CPUs get squashed closer together. So you might get frequency improvements, you'll get latency improvements. So there are second order benefits of that. You have to take all of that into account when you're modeling to see what system performance improvements you get. So these are the three factors you need to consider, which is phi area, cost, and performance, whether to keep it on die or bring it off die. I've taken an example, a real example. This is an example of a Grok AI inference chip. You can see one of their die shot, which is like about 40% is just SRAMs. About 220 megabytes of SRAM. That's huge on a chip. And each chip goes on a single card. The card goes into a cluster. It's called the node, funnily. And then you rack mount it. And each one of these cards are connected to other cards in a topology using optical cables. And so if you wanted to do inference on a 7 billion parameter model using the traditional existing chip, that would mean you'd need to connect about 70 of these cards together. and all the optical cables. We've done some calculations, 1.9 miles of optical cables. I'll fast forward to 10 trillion parameter model, which is where people might head in the future. So more higher parameter models. You would need to physically connect 100,000 of these chips. There is no way you can connect them and statically schedule inference for it. There is no way. You can't do it. And look at the amount of miles of cables you're connecting in one single data center. But a simple change, and the reason why that is the case is because the Grok architecture is 100% SRAM, and the number of chips you need to connect is directly proportional to the memory available on chip. So if you unlock more memory on a package, which is vertically stacking, you can potentially get an order of magnitude reduction in the number of chips you need to connect via optical cables. And then you get second order benefits, which is not just the more memory on chip, but the less optical cables, which means the less latency at the system level. I feel sorry for the person who has to connect all these optical cables and make sure it works. So final slide, which is 3 examples of SRAM memory chiplet. So 16 MB, 64 MB, 128 MB. Shows how big the size of the chip is. So for example, a 16 MB chiplet made in a 7 nanometer process is about 5 millimeter square rounded. But the phi area would be 0.02 millimeter square, which is, you can round it to 0. So pretty much no penalty on the area on your chip unlocks 5 millimeter square worth of memory, vertically stacked, which would have previously been on the same chip traditionally. And then the renders below show how you can imagine on vertically stacking. So there's no one way of vertically stacking chips. You could stack them as a mesh. You could stack them on top of each other in the middle. You could stack them on a smaller mesh. So now it's up to the imagination of the chip architects and designers on how they can reimagine the compute architectures where the memory is just gone out of the way. And on that note, I'll let you decide for yourself whether SRAM is dead or alive. Thank you.
Thank you. We've got time for a couple of questions if there are any for Carol.
2 minutes, go. Yes.
Sorry, how many fabs are able to do these?
Pretty much all the big fabs. So Samsung, yes. TSMC, obviously, yes. Global Foundries, yes. Intel, obviously, yes. Even smaller fabs are able to do 3D integration. So 3D integration can be done even on 180 nanometers.
Are they using a standardized system that we can go to one fab and have it done there, but when we change our minds, you go to another fab and have it, and you don't have to redesign things?
So that's the impediment, which is multi-foundry does not exist today. So if you wanted to do multi-foundry 3D integration, that is completely non-existent, which is what is one of our missions to overcome as a company.
Great, thanks very much. Apparently we've been summoned to the main it might be pizza.